So today, we are diving into something you see literally every single day, but probably don't think twice about: liquids. It turns out, from a simple drop of rain to that stubborn stuff in a bottle, they're all following a hidden set of rules that are, well, they're bizarre and totally fascinating. Let's get into it. You know the scene. You've got the bottle upside down, you're tapping it, maybe you're pleading with it, and absolutely nothing happens. Then all of a sudden, whoosh, it all comes out at once. So, what is going on inside that bottle? This one simple, kind of frustrating question, that's our doorway into the super weird world of fluid physics. Okay, so to understand why some liquids, like our friend ketchup, seem to misbehave, we first have to get a handle on what makes a normal liquid behave in the first place. And to do that, we need to shrink way, way down to the level of molecules. Right, so the key thing to get here is this perfect balance. Unlike a solid, a liquid's molecules aren't all locked into place. They've got freedom, they can flow. But unlike a gas, they're not just flying all over the room. They're still packed in pretty close, held together by these invisible forces. It's this special mix of connection and freedom that gives liquids all their unique properties. And this slide just lays it out perfectly. Think of a solid like a perfectly choreographed dance team, right? Everyone has their spot. A gas? That's more like a chaotic mosh pit where people are miles apart. But a liquid? Now that's a crowded dance floor. Everyone's packed in tight, but they can still shimmy and slide right past each other. So what's the physics behind that crowded dance floor? Well, you've got these things called intermolecular forces, which are basically like little magnets trying to pull all the molecules together and create some order. But at the exact same time, you've got entropic forces, which is really just nature's love of chaos pushing them apart. In a liquid, these two forces are locked in a perfect tug of war, and that constant battle is the secret to everything. And that brings us to our first amazing liquid property. Because of that molecular tug of war, liquids have something that acts like an invisible, elastic skin. It's a property we call surface tension, and it is so cool. Okay, so here's how it works. Imagine you're a molecule deep inside a glass of water. You're being pulled on equally from all sides by your neighbors. It's all balanced. But what if you're a molecule right at the surface? Well, you're only getting pulled from below and from the sides. There's nothing above you. This imbalance creates this powerful inward pull that squeezes all the surface molecules together into a tight web. And this is just the perfect way to picture it. The top of the water isn't just a boundary, it's this dynamic, tension-filled layer. It really does behave like a sheet of spandex stretched tight over the top. And this elastic membrane is responsible for some seriously amazing stuff. For instance, have you ever wondered why water beads up on a leaf or a freshly waxed car? That's surface tension. The water molecules are just way more attracted to each other than they are to the waxy surface. So, to keep as many of their buddies happy as possible, the liquid pulls itself into the shape with the smallest possible surface area, which for any given volume is a sphere. You see the exact same thing with a dripping faucet. As the water hangs there, gravity starts to stretch it out. But eventually, that elastic skin gets strong enough to say, nope, and it pinches itself off, snapping the water back into an almost perfect little sphere as it falls through the air. And of course, the most famous example, it lets insects like the water strider literally walk on water. Their feet actually press down and dent the surface, kind of like you would on a trampoline. That stretched elastic skin pushes right back, and it's strong enough to support the insect's weight. So they aren't floating in the water, they are being held up by it. And the whole reason we see these things so clearly with water is because its surface tension is incredibly high. Thanks to these really strong connections between its molecules, called hydrogen bonds, water's elastic skin is one of the toughest around. Okay, so we've learned the rules for normal, or what scientists call Newtonian liquids. They've got this awesome surface tension and their flowiness is pretty consistent. But now it's time to get back to our ketchup problem and talk about the rebels, the fluids that love to break the rules. So the key property we need to talk about now is viscosity. It's really just a fancy word for a liquid's internal friction, or, its thickness. Honey has super high viscosity, which is why it pours so slowly. Water has low viscosity, so it flows really easily. For most liquids, this number is a constant. And that right there is the huge difference. For a Newtonian fluid like water, its viscosity never changes. It flows the same whether you stir it gently or you whisk it like crazy. But for a non-Newtonian fluid, applying force, what scientists call stress, actually changes its viscosity. The thickness itself changes. This chart just shows it all perfectly. Look at the bar for the Newtonian fluid. Its thickness, its viscosity stays flat, constant. But then you have the rule breakers. Shear thinning fluids, like our ketchup, actually get less viscous when you apply force. See how the bar goes down? And then shear thickening fluids do the exact opposite. They get more viscous. That bar goes way up. And there it is, the answer to our original mystery. Ketchup is a classic shear thinning fluid. When it's just sitting there in the bottle, it's really thick, super high viscosity. But when you shake it or whack the bottom of the bottle, you're applying stress. That stress dramatically lowers its viscosity, and it suddenly gets all runny. It's the same idea with paint. It flows easily when you're brushing it on, but then it thickens up on the wall so it doesn't drip.
But then you've got the total opposite, shear thickening fluids. The most famous one is oobleck, which is just a simple mix of cornstarch and water. If you move your hand through it slowly, it feels like a liquid, no problem. But if you try to punch it or slap it, it instantly becomes hard as a rock. The force you apply makes its viscosity shoot through the roof.
And you can absolutely experience this incredible science for yourself. Seriously, it's so easy to make. Just mix up some cornstarch and water with these ratios. When you play with it, you can literally feel the liquid transform into a solid and back again, right in your hands. Trust me, it's a feeling you will not forget. So let's bring this all home. We've gone from the tiny dance of molecules to the invisible skin on a drop of water, all the way to fluids that can change their very nature right before your eyes. The main thing to take away here is that our everyday world is just packed with these hidden rules. That perfect little sphere of dew on a leaf is governed by the exact same surface tension that lets an insect walk on water. And that frustration you feel with a ketchup bottle, that's you having a direct, personal interaction with the bizarre, rule-breaking world of non-Newtonian physics. Because once you start looking for this stuff, you see these principles everywhere. In the kitchen, in your own body, out in nature. It really makes you wonder, what other incredible liquid secrets are we just totally overlooking every single day? Thanks for listening.